Now, first of all, when it comes to scale up, you want to ask, why bother scaling it up? Is this just a case of making something bigger for no particular reason, rather like you making a bigger car for no particular reason? Well, I hope to show you that that's not the case with CCC. There are plenty of really excellent reasons why you might be interested in scaling up CCC. Here are some of them. Laboratory scale centrifuges can separate large quantities of material from a few milligrams to up to 10 grams or more. So you can separate out large quantities with only a small machine. You do not need a pilot plant, you do not need a manufacturing plant in order to get preparative quantities of material, as you do with other forms of chromatography. You use significantly less solvent than with Prep HPLC, so it's more economical. You get a very high sample loading. From 70 to 90% of your column is the stationary phase. And that's a very large percentage compared to HPLC, and that is the reason why you can do large quantities on a small machine. It can cope with crude extracts and particulates. Now that's an advantage even on a small scale, but on a large scale it is an even bigger advantage because you don't have to go through a complex filtering process. If you have a kilo of material and you're trying to filter, you could lose a lot of material. It can be very, very difficult. It can be expensive to filter. You can choose how to operate it. Now this is a great strength when it comes to preparative. You can use it in reverse phase mode or normal phase mode, or switch between the two. It is predictable and it's reproducible. That means that each time you come to a CCC machine and do your preparative run, you're effectively making a fresh column, which means your peaks will always come out at the same time. You're not getting any of this drifting of peak retention time or gradual merging of two peaks into one as a chromatography column declines. So that predictability and reproducibility is a real advantage when you're trying to do preparative runs or when you're doing lots of runs. And you also don't get any cross-contamination between, there's no adsorption on the column. So when you change from one project to another, you don't get this cross-contamination. With Prep HPLC, a lot of companies will have a Prep HPLC column for one project and another column for another project and a third column for a third project in order to avoid the danger of cross-contamination. You don't need to do that with preparative CCC. And so in total, and I've already mentioned this, it is more attractive from a regulatory point of view because the consistency, the lack of cross-contamination, the loading, all means that from a regulatory point of view, CCC has a tremendous advantages when you scale it up. Now when you're talking of scale up, the two important factors are how fast you do your run and how much you can load on each run. The faster you can do your run, the more runs you can do in a day, the quicker your separation is, the more you can load, the more you get done per run. Now your speed times your load, the product of the two, is your throughput. That's how much material you process, how much pure material you create in a day or a week. Now, when you produce a graph of speed against load, here you have the speed from low to high along the axis and from low to high on the vertical axis. HPLC, preparative HPLC, sits about there. In other words, the speed is moderate, it's okay, but the loading is poor. It's a very low loading on Prep HPLC. If you go to normal phase HPLC, the speed is about the same, but the loading is slightly better. You can actually put more material onto normal phase chromatography. Flash chromatography is even better. You can see that you can load even higher amounts on. If you want to increase the speed of your HPLC, you can go for supercritical fluid chromatography, where the lower, less viscous mobile phase means you can push through higher flow rates, so you increase the speed. Now, you'll see at this point here, there's a hole in the graph about there, and that is where I want to place high speed or high performance CCC. Now here I'm talking about high loadings and high speeds, and this is for talking about the high performance machines. So the high performance machines do very fast runs and they have high loadings as well, and that's where CCC fits in for the preparative scale. So which one do we scale up? We've talked about hydrodynamic and we've talked about hydrostatic CCC. Which one do we scale up? Now, as a brief bit of revision, I'm sure you all know this by now, the hydrostatic CPC, centrifugal partition chromatography, has a whole lot of interconnected chambers and it is spun on a single axis. The mixing inside those chambers is a cascade mixing, just a sort of a jet of one liquid in through the other. On the other side is the hydrodynamic, which is spun in planetary motion and is a single coiled tube. The mixing inside the hydrodynamic is a wave mixing. The important point why it's called a hydrostatic machine is that if you are spinning a hydrostatic machine and you switch off the pump, the mobile phase pump, then your stationary phase stays where it is. It is trapped in the little chambers. So your stationary phase is held in place by the design of the machine, and that's why it's called hydrostatic. The mass transfer occurs in each of those little chambers. That says pretty much the same thing. The hydrodynamic behavior occurs in each chamber. And the most common form is the centrifugal partition chromatograph, where there is a series of interconnecting chambers and it spins on a single axis. But you need to remember that rotating seals are required. So that's a summary of the hydrostatic machine. In contrast, the hydrodynamic machine, if you're spinning a hydrodynamic machine and you switch off the pump, the flow, the phases inside will distribute themselves to each end of the coil. The heavier phase will go to the tail of the coil and the lighter phase will go to the head of the coil. So even though you're not pumping anything, if the spin stays and you stop the flow rate, the phases distribute themselves to each end of the coil, and that's why it's called hydrodynamic. So that means that the volume of stationary phase retained in a hydrodynamic machine is very dependent on the mobile phase flow rate, whereas in a hydrostatic machine it was less dependent on the flow rate. The mass transfer is via a wave mixing that occurs within each coil, in each coil loop. And the most common form is the J-type centrifuge, which we've been talking about a lot, the J-type CCC. But no rotating seals are required. You do have flying leads, but there are no rotating seals on the hydrodynamic machines. Now in this talk, I'm going to be talking about scale-up of the hydrodynamic CCC, hydrodynamic countercurrent chromatography. Although this is probably, there might be some debatable points in here, we believe at Brunel University that there are challenges with scaling up the hydrostatic machines. One of them, with a hydrostatic machine, the pressure is quite large, and when you scale it up, you can get some very high pressures. Remember, you've got rotating seals at either side, and higher pressures give you a higher challenge, a bigger challenge to keep those rotating seals with high integrity. Another challenge is the cleaning and the cross-contamination issue. If you're going to use your preparative machine for manufacturing scale runs, pilot scale runs, then you want to ensure that you're not getting any cross-contamination. And if you have hundreds of little chambers, how do you ensure that you're not getting some cross-contamination from one project to another, or one compound to another? So that's another one. It'll be harder to satisfy regulatory authorities that you've cleaned the machine properly. The removal of air on large CPC machines can be difficult. You've got all those little chambers, and trying to get all of the air out of it can be quite a challenge, and air adds another complication into your separation. And finally, it cannot cope with particulates. With all hydrostatic machines, you've got the chambers are okay, but you've got these connecting tubes, and the connecting tubes can easily block with particulates. So for those reasons, we think that the hydrodynamic machines are the ones that is going to be more interesting for when it comes to the scale-up, particularly if you're scaling up to preparative, pilot, and manufacturing levels. So I'm going to talk about the scale-up of hydrodynamic countercurrent chromatography. These are the machines that we have at Brunel University. This is our smallest machine, known as the Mini. You can see the specification there, and I've also got the specification in these brochures here. We don't sell the machines, I have to say. The machines are largely sold by dynamic extractions, but these are the machines that we have within our bioprocessing centre, and I've copied the table with the specifications in here. You're welcome to pick up these leaflets. The Mini CCC machine, this one here, has a 17 milliliter volume recoil, 0.8 millimeter bore, spins at 2,100 revs per minute. High G-force spin. There's reasons for that, which I will go into detail later in my talk, why it's a high G-force machine. But 2,100 revs per minute. Typical separation time will be about 20 minutes for a peak with a distribution ratio of 1. And typical loading on this machine will be anything from 5 to 30 to even up to 50 milligrams on a machine this size. As you can see, it's about the size of a microwave oven. Now, to be able to inject 50 milligrams on a machine this size is quite impressive. Because on a HPLC, you'd need quite a large HPLC to be able to do that. This is the middle-sized machine. The volume here is 930, so almost a litre. The coil bore, you can see, is 3.6 millimeters. Spin speed 1,400 revs per minute. You don't need to spin so fast because you have a greater radius for your spin, so you can get the same G-force with a lower rate of spin. So it's 1,400. Typical flow rate is, we would use it typically at around about 50 milliliters a minute. Same sort of runtime, 20 minutes for a distribution ratio of 1 peak. And the loading on this will be anything from 5 to 25 grams of material. So definitely a preparative machine. This is the 5-litre machine. The coil bore, you can see, is 10 millimeters. Maximum spin speed is 850 revs per minute, but we typically run it at around about 650 because we don't need to go up to 850. I'll show you why in my presentation. Flow rate range is usually around about 600 mils a minute. Still the same runtime, 20 minutes. So still the same runtime for D equals 1 peak. And we can inject anything up to around about 300, 350 grams on this machine. And the biggest machine that we've got is this one here, 18-litre machine. Same bore size, 10 millimeters, same spin speed, and we tend to spin this one at around about 500, 600 revs per minute. Flow rate is anything up to 3 litres a minute, but typically we'll use it at maybe 1 litre a minute flow rate. Same run time, notice, 20 minutes run time, and we can inject up to 1 kilogram of material per run on this particular machine. All of these machines are housed in the Bioprocessing Centre at Brunel University. Any of you are welcome to come and visit us. We're a research centre. We don't have any secrets in the machinery and what we've got in the Bioprocessing Centre. And I would suggest a good plan would be to come to the conference at Lyon in July. And London is only a short trip away, and I'll be I'm happy to see any of you and I'll show you around the centre, show you the machine, and we can even look at seeing how you could do some separations. So this is the Bioprocessing Centre. It consists of 5 laboratories. So we've got 5 laboratories just purely researching countercurrent chromatography. And within there, this is the pilot scale laboratory, the hazards lab we call it. What you can see there is the 5-litre machine. On the right-hand side is the pumping system, and what you can't see is the 18-litre machine over the other side, that's out of the picture. In the front is a computer, a laptop with the software that runs the machines. But the important point about this particular operation here is that the computer is in a different room. It's in an operator room. You're taking the picture through a sheet of explosion-proof glass. All of the equipment in that room is remotely operated. You put protective equipment on, such as the usual lab coat and gloves and mask if necessary, in order to go into the room to set up the machines, to put your sample, to load your sample, to put the solvent systems in place and so on. But once you've done all the setting up of the machines, you then come out of that room, shut the door, and you go into the operator room, and you can then run the machines from the operator room. And here is one of my colleagues, Peter Hewitson, doing a run. So he is performing a CCC run on the large preparative machine. So it's entirely operated from the operator room. The nice thing with the operator room is it is a clean room. You can take your cup of tea in there and your sandwiches. Yeah? The software was designed specially for us. It was a modification that Armand did for us. I don't need to go through details of the software. Here are the two CCC machines. Yeah? This is a 6-head pump, which is the elution pump. 3 of the heads will pump one phase, and 3 of the heads will pump the other phase. So we get a nice smooth flow with 3 heads, but we can very quickly switch from one phase to the other. And we've got all this complicated valving system in order to be able to do that. We have another pump here in order to introduce the sample. That's, we can introduce a sample from the upper phase, from the lower phase, or from both if necessary, using this other 6-headed pump. There are 2 detectors. We've got the whole flow goes through a UV detector, but then we've also got a bleed to a light scattering detector to make sure we don't miss any components. And then we've got the fraction collector just down here, so we can collect all the fractions. So it's quite a good system with a good bit of flexibility in how we operate it. Now, let's talk a little bit about the theory of the scale-up. You've seen this diagram several times. Basically, the more stationary phase you retain in your CCC coil, the better resolution you get. So a lot of effort goes into trying to retain a high percentage of stationary phase in the coil. Now, as you know, when you increase the flow rate, you get less stationary phase in your coil. You just push more of the stationary phase out. This is a plot known as the dew plot from the person who discovered it. What you have is the percentage stationary phase retention from 0 to 100, and along the bottom is the flow rate that has been squared. It's the square of the flow rate, because then you get a linear relationship between the stationary phase retention and the flow rate. So this is a point here is at 2.2. That'll be a flow rate of 5 mils a minute. This is 10 mils a minute, 20, 40, 80 mils a minute. And you get a linear flow rate, but you get a drop of stationary phase retention as you increase the flow rate. That's as you would expect. Now, this is the line from the previous graph. However, if you increase the bore of the column, in other words, you make your column with a wider bore, this effect gets less. You get less drop in stationary phase retention with flow rate. So this one here is with a column bore of 3.73 millimeters. When you increase the bore to 5.83 millimeters, the effect is less. When you increase it to 7.73 millimeters, it's even less. So your stationary phase is more stable in the column with a greater bore, with a bigger bore. The breakthrough in understanding, and this produced a paper which I've referenced down here, was that the amount of mobile phase stays the same. But when your bore increases, that means that proportionally you have more stationary phase. And that was the breakthrough in understanding. Here's the effect it has, and I like to claim that this slide shows that scale up with CCC, it's better. It gets better the bigger you make it. Here's 4 CCC instruments. There's the MIDI with a small bore of 1.6 millimeters, a wide bore MIDI with 3.7 millimeters, and the Max T with 10 millimeters. So you've got 0.8, 1.6, 3.7, and 10 millimeters bore. So that's the bore of the coil. Those are the machines down here. In the table here is the flow rate that is required to get the stationary phase retention that is up here. So if we start off in this box here, on the mini machine, on this smallest machine with a 0.8 millimeter bore, in order to get 70% stationary phase retention for this particular phase system, you will need 0.66 milliliters per minute flow rate. Now, if you say, well, I want to scale up now to 1.6 bore, and you do the calculations and say, what flow rate do I need to get the same stationary phase retention on a 1.6 millimeter bore, the calculations will tell you 1.8 mils a minute. When you do 1.8 mils a minute, when you go into the labs and actually type in 1.8 mils a minute on this machine, you don't get 70%, you get 85% stationary phase retention. So you think, okay, I can up the flow rate. How much can I up it? Well, you can up the flow rate as much as 7.2 mils a minute, and you then get your 70% stationary phase retention. Again, you can do the calculation and say, well, I now want to go onto the bigger machine, the wide bore mini of 3.7. The calculations will say 10.2 mils a minute will give you 70% stationary phase retention. In actual fact, you can have 92 mils. Yeah? And likewise, when you go up to 10 mils a minute, calculations say you will need to go 84 mils a minute. But in actual fact, you can go up to 1.3 liters a minute. So you are less likely to push your stationary phase out when you go for a bigger bore. So the machine is more stable. The bigger machines are more stable. Now, I've talked quite a bit about the G-force. I've mentioned high G-force machines. The reason is fairly obviously that, when you have a high G-force machine, you are more likely to retain your liquid stationary phase. Your machine becomes more stable. Here again you have the stationary phase retention from 0 to 100. Here again you have the flow rate that has been squared. So this is a dew plot, and this is one for 800 revs per minute on this particular column, and this is what happens when you spin it at 1200 revs per minute. You can see that you get an increase in stationary phase retention of about 10% for the increase in spin speed. So spin the machine faster and you can retain the liquid stationary phase better. That's as you'd expect. But when it comes to scale up, you also get higher throughput when you spin the machines faster. Here we have the sample throughput. Now this is in milliliters injected per hour. Yeah, so that's the sample throughput, how much we do per day of injections or sample. And here's the flow rate. This time the flow rate is just straight in milliliters per minute. This curve here is at 800 revs per minute. This one here at 1000 revs per minute, and this one here at 1200. You can see that at 40 mils a minute, it doesn't make much difference what the spin speed is. It's about the same for all three of them. But when you come to 120 mils a minute, you have 700 milliliters injected per hour or at 800 revs per minute, or you can raise that up to 1100 milliliters per hour injected at the higher spin speed, 1200. When you come up to 160 mils a minute, then basically you start losing it all at the lower spin speed. But you're still increasing in your sample throughput, not much, it's plateaued a bit, but still increasing slightly at the higher spin speed. So you get much better throughput of sample at your higher spin speed. You might say that a higher flow rate to give you higher, in order to give you a higher throughput, might mean that you get more sample through, but you lose your resolution. Well, you do, but not by very much. This is on a wider bore column, 5.53 millimeters, and this is an injection of two standard compounds, benzyl alcohol and paracresol, I mentioned, and this is at 10 mils a minute, and you can see you get almost baseline resolution. 20 mils a minute, 40 mils a minute, 80 mils a minute. There is a loss of resolution, But it's not a huge loss of resolution, and you're getting considerably faster throughput of sample. So the wider bore columns retain the stationary phase better, you can inject more sample, you can drive them harder, and you don't get much loss of resolution. Here you have the decrease in resolution, showing that the wider bore the wider your column bore, the larger your column bore, the less your resolution declines when you increase the flow rate. Here you have resolution of 2 peaks. Here you have the mobile phase flow rate in this is in liters per minute. And here you have it for 4 different column bores. The blue line, the dark blue line, is for a column bore of 3.73 millimeters. So you can see that as you increase the flow rate, your resolution drops dramatically. You just lose your resolution completely. So if you have a small bore column, you need to run it really slow. Otherwise you get very poor resolution. When you go up to 10 mils a minute, as you increase the flow rate over a very wide range, you don't get that much of a drop in resolution. The line is fairly stable. So a wider bore, you can increase the flow rate and you don't lose your resolution very much. And the wider you make the bore of the column, the more you can increase the flow rate and the less you lose in your resolution. This slide here, I'm just asking the question, which is better? Is it better to inject your sample with high concentration and low volume, or is it better to inject it with low concentration and high volume? Here are the benzyl alcohol and paracresol injected. The solid line is high concentration and low volume. The concentration was 42 grams per litre benzyl alcohol, 20 grams per litre paracresol, and 290 milliliters was injected onto the 18-litre machine. The dashed line here is 12 grams per litre benzyl alcohol, 6 grams per litre paracresol in 960 mils. So the same amount was injected, but a much larger volume. And you can see from the dashed line that the join of the peaks is slightly higher, so the resolution is slightly better for high concentration, low volume. So if you're going to do an injection, you can see the resolution is 1.01 here and 0.83 there. So with preparative separations, high concentration, low volume is better, so long as your high concentration is not so concentrated it emulsifies your two-phase system. Now, I have talked about all the advantages of scaling up CCC, making it bigger, and you seem to win in almost every respect when you make it bigger. What's the downside? Well, the only downside is really the engineering challenges that occur. When you scale it up, you get much more friction in the bearings. You've got bigger mass that's spinning. It's going to generate more heat. Your flying leads become thicker because you're flying more through it, and the flying leads might not last quite so long. You've got to have precise gears. You've got more mass that's spinning. You've got to make sure the gears are strong enough, and you've got to make sure that you keep the noise down as well, because a big machine could be extremely noisy. And also, when it comes to manufacturing a pilot plant, people want machines that can do continuous or semi-continuous running with minimum breakdowns. So the only real downside to the scale-up are the engineering challenges. So as an application scientist, I just say over to you engineers, sort it out. Yeah? Because as far as I'm concerned, scale it up and it gets better. So as an interim conclusion, just a sort of mini summary. The retention, stationary phase retention, increases when you increase the rotational speed. It also increases when you increase the tubing bore of your coil, and it decreases when you increase the flow rate. But if you have a large bore column, it is much more tolerant to the increase in flow rate. Yeah? Resolution does decrease with increasing flow, but it only does so gradually, and even less so when you use the wide bore columns. So therefore, there is plenty of scope yet for the further scale up of CCC, and according to the engineers, it is still behaving. Our 18-litre machine has been shown to theoretically allow a 40-litre machine to be made, and they can prove that that will still work entirely predictably. So the flow is still predictable, the behavior inside the coils is still predictable, and so we haven't reached the limit of the scale up yet. A 40-litre machine is possible. How much bigger can it go? Well, I don't know. That's the end of the little section on the theory of scale up. I'm now going to talk about solvent recycling, and then I'm going to talk about some modes of operation, some different modes of operation of scale up, which might be interesting. Solvent recycling. When you come to large scale preparative countercurrent chromatography, you can't make up your two-phase system in a separating funnel in a fume cupboard, separate out your two phases. You can't throw away all the solvent because you're talking quite large quantities. So solvent recycling becomes important. This is the solvent table that I presented in my last talk. I've seen it's been printed in your booklet. If you selected one of those solvent systems, say we select solvent system number 12, you can't make up that solvent system in a separating funnel when you're on a preparative machine. The 18-litre machine has a flow rate of maybe a litre per minute. If you were going to do a 30-minute run, that would be 30 litres of solvent. You can't shake up 30 litres in a fume cupboard. So what do? Well, we have analysed the composition of each phase. So this is the composition of the upper phase. So this is the same table, and solvent system number 12, if we pick that, we would make the upper phase by putting in together 2.8% of methanol, 69.6% ethyl acetate, 26.7% of heptane, and 0.88% of water. And that would make the composition of the upper phase. So we could make it up as much as we needed. And here's the composition of the lower phase. So for our system 12, we would put 22% methanol, 10% ethyl acetate, no heptane, no butanol, 67.6% water. And that would make up the composition of the lower phase. So we just make up the phases to demand. Of course, having done that, you can look at what's actually happening in the solvent system with the different components. This is the upper layer composition, and you can see that as we go more polar, remember this one here is very polar, and this one here is very non-polar, you can see that you get an increase in heptane and a decrease in ethyl acetate. And there you can see much the same thing with the lower phase. You can see as you go more non-polar, you get an increase in methanol and a decrease in water. But there are two advantages to analysing the phase system. The first is we make up as much upper phase as we need and as much lower phase as we need. We make it up to order, using that composition table from the analysis. The second advantage is we recycle the phase. So when we've done a run, we collect the fractions, you dry the fractions down, you're going to do that anyway. We take the solvent out of the rotary evaporator, we just do a quick analysis on the gas chromatograph, and then we reform the composition back into the composition of the mobile phase, and it goes back into the machine for the next run. So there's a recycling of the phase. What we tend to find is if you're using a hexane ethyl acetate methanol water system and you're using the hexane ethyl acetate phase as the mobile phase, then the chances are you will have just lost a bit of hexane. That's usually all you need to top up, is just a touch of hexane, and it can go back into the machine. but we remake the solvent phase back as it was. And this shows two chromatograms, one made up with fresh solvents, the other one made up with a recycled, reconstituted mobile phase, and you can see there's no difference between them. These were done on the 5-litre machine. Notice that this is 20 minutes. Okay? So you can see that the whole run was 23 minutes. So although it's a preparative run, they're still very fast. So this will be a typical protocol for the 5-litre machine. In this case, we're using this solvent system here. The injection in this case was 150 grams in that material. That amount is 5% of column volume. The run time was 20 minutes. Recycled in cycling time in 35 minutes. In other words, the run finished in 20, but it then took another 15 minutes before the machine was ready for the next run for dealing with fractions or whatever. That's the flow rate. And 12 litres of solvent are used per run, but 9 litres of that is recycled. The only reason that the other 3 litres aren't recycled is that those fractions were just so grotty that it wasn't worth the effort of drying down the solvent. We just decided we'd sacrifice 3 litres of solvent per run. You could recycle the whole lot, but you've just got to dry down the whole lot. And we decided they were so mucky that it wasn't worth it. So that is a typical protocol. A large percentage of the solvent is actually recycled during the run. Now, I talked a little bit about injection loading. Here's a bit more details. This particular example for injection loading is a separation of these two compounds, honocule and magnolol, both natural products from Chinese medicines. The only difference between them is the location of this hydroxyl group here, which has just changed its position, so they're isomers. When we were doing this run, we started off injecting 20 mg per mil on the 5-litre machine, so 4.6 litre machine. So 20 mg per mil was injected. And that gave this chromatogram here. There's one compound, there's the other. 30 minutes is here. We got good separation, really good separation, small peaks. And we thought we're obviously not loading the column enough. So we went 4 times bigger and injected 80 mg per mil. That gave this chromatogram here, obviously considerably more compound as eluted, and we've still got almost baseline resolution between the two components. So we thought, well, we haven't reached the limit yet. Let's go the whole hog, and we injected all the rest of the sample at 320 mg per mil. And we got this single peak. And we thought, notice it's come off in 16 minutes. So we got a single peak come off. We thought, oh dear, we've blown it. Yeah, we've just gone and achieved nothing. The sample has come off in a single peak. But fractions were taken across that peak, and here's all the fractions. And here you can see the analysis of the fractions from that big peak. So the brown line is the magnolol, and this purple line is the honocule at that injection of 320 mg per mil. And you can see here is the brown line, and here's the purple line, and you can see that you've got not a bad separation, even though it came off as a single peak. So the separation occurred, even though on the when we looked at it, we thought we'd actually just blown it and come off as a single peak. Now, for the rest of my talk, I'm going to talk about 3 special modes of operation. So far, we have talked about standard, I suppose, traditional countercurrent chromatography. This is hydrodynamic countercurrent chromatography, where you have just a simple coiled tube that is spun in the planetary motion, creating those waves of mixing and settling. Now, being a research centre at Brunel University, we're interested in trying to find ways that might be more efficient, ways that might be better than doing that. And I'm going to talk about 3 special ways of operating countercurrent chromatography with particular respect to improving the scale up, to making it, to getting better throughput of compounds. And the first I'm going to talk about is toroidal coil CCC. And this is particularly going to be particularly interesting for the purification of biomolecules. Normally, CPC the one with all the little chambers, hydrostatic CPC is used for the purification of proteins and DNA and plasmids and viruses and for biomolecules, because the stationary phase can be retained in the coil by being trapped in those little chambers. However, industry doesn't like CPC very much because of the reasons I mentioned earlier, the danger of cross-contamination, the difficulties in scale-up, and so on. So we have made this machine, which is a toroidal coil. It was initially invented by Dr. Ito, but we have created this as a toroidal coil machine, which has the advantages of the hydrodynamic CCC, but can also separate out the biomolecules. The way it works is your coil, instead of just being coiled round like this in a multi-layer coil, is coiled round like this and then like that. So it's almost like taking a hollow telephone cable and wrapping it around in a coil. Yeah? And then it is spun in the normal planetary motion. Now, as you can imagine, some fairly complex mixing goes on inside there. But the bottom line of it is that the mixing that occurs inside the toroidal coil machine is the cascade mixing that occurs in the CPC machine, not the wave mixing that occurs in the multi-layer CCC machine. So we've basically created here a CCC machine with a single tube wound in this toroidal coil manner. It's got a single tube, but it's got that cascade mixing. So how does it perform? Here we have the injection of two proteins. If you look on the green line first, this is lysozyme and myoglobin, two proteins, and separation has occurred here with just one bobbin, and this is a separation with two bobbins. Both there were two bobbins on the machine, so you get slightly better resolution with the two bobbins for a longer time. The separation here is about the same performance as would occur on a CPC machine. The reason why we think that the toroidal coil is going to be important for scale-up is that because it's just a single tube, you can clean it easily, you can deal with the particulates, it can be scaled up. We found that when you're putting the aqueous two-phase systems required for proteins into a multi-layer CCC coil, we could retain the liquid stationary phase very easily. That wasn't a problem, but we still didn't get very good separation. The reason why we didn't get very good separation was because we weren't getting good mixing of the two phases. The wave mixing works very well when you have aqueous organic solvent systems. It doesn't work so well when you've got viscous systems, such as the aqueous two-phase systems. So the different mixing of the toroidal coil machine solved that problem. We get both the retention and the mixing, and therefore we get the separation of the proteins. And here we've basically increased the scale length in order to give better resolution, and the resolution has increased as predicted with CCC theory. You would predict that for every doubling of the coil length, you will get a √2 increase in the resolution. The resolution is proportional to the square root of the coil length. So you double the coil length, you get a √2 improvement in resolution, or 1.4 times. And that is exactly what we see here. So it's behaving as predicted by CCC theory. However, what's interesting here, here's the resolution, again in the toroidal coil machine. Here is the rotational speed. As you increase the rotational speed, we get an increase in resolution. But then it plateaus. Now, that was puzzling us a little for a while. Then we realized in the toroidal coil machine, you have these loops. Remember, they go round like this and then they go round in the coil. You have the loops. Yeah? As the machine spins in its planetary motion, the mobile phase at a low spin speed will run round the walls those loops. It'll actually just stay stuck on the walls and will run around the walls. As you increase the spin speed, you pull that mobile phase away from the walls and it starts going down the middle of the tube, and you get much better mixing. So as you increase the spin speed, more of the mobile phase is pulled away from the walls by the g-forces, and you then get it passing down the middle of the tube, but then you don't get any further improvement because the mobile phase is jetting down the middle of the toroids. So that is the theory as to why we get this plateau in resolution at a certain spin speed. So for the toroidal coil machine, there is an optimum spin speed, and on our particular machine, there is no point in us running it more than 1200 revs per minute. That's different from the normal multi-layer CCC. This slide here shows the big advantage of the toroidal coil machine. You have a run where you've got something coming off the solvent front. Here's separation of the two proteins, lysozyme and myoglobin, we did before. This line here shows the eluted volume. So this is what was coming out at the end of the coil. And as you'd expect, you've got just a standard linear line because we kept the same flow rate all the time. But the orange line is the amount of eluted stationary phase, and the purple line is the amount of eluted mobile phase. You can see that when we started the run, we get stationary phase coming out at first, as you'd expect. You fill the coil with stationary phase, you start pumping, you start the spin, start the mobile phase. You push out a certain volume of stationary phase, but then no more stationary phase came out. None of it. The thing was very, very stable. In other words, there was no bleed of stationary phase, and that is a big advantage because with CPC, you often get a bleed of stationary phase coming out. So overall, this toroidal coil machine is, we think, going to be very useful for the scale-up of biomolecules and proteins and other fragile molecules that don't like aqueous organic phase systems. It has advantages over CPC machines in that you don't get any stationary phase bleed. You have much higher loadings. We calculated that you get about a 42% increase in throughput with the toroidal coil machine over a CPC machine. It is scalable. There is no reason at all why the toroidal coil machine can't be made up to 5 litres, 18 litres, 40 litres. It is scalable, whereas the CPC machines have challenges in scale-up. And finally, it's got the advantages over CPC, and it's easy to clean, you can sterilize it, and it can cope with particulates as well. So the toroidal coil machine might well be the future for the scale-up of biomolecules and proteins. Now going on to special mode of operation number 2, non-synchronous CCC, and this is for the perfect mixing and settling of solvent systems. Now, so far, we have talked about the synchronous CCC, J-type chromatographs. Called J-type, of course, because of the leads just here. And you have a stationary sun gear, and you have a rotating planetary gear, and this rotates around like this, and so that it spins on its own axis, and it rotates around the stationary sun gear. As you know, the leads don't twist up. I'm sure you've seen it in the model, and you've seen it actually in the lab. It's a little bit difficult to get your head around why the leads don't twist up. It's a little bit difficult to actually work it out. I quite like this picture showing why it is that leads don't twist up. Imagine you have a dumbbell, a bit like people use for weights, yeah? But this has got a rubber handle. If you rotate that dumbbell, you can see that this will rotate the same as that. No problem there. Now keeping it the rotating there, you just bend the handle, bend it over, and you will now have the two rotating like this, still with your handle in the center. And that is why the leads don't twist up. Here we've got both rotating, but what we could do is you could hold that one and just rotate this one around it. And there's your J-type CCC machine. That's why the leads don't twist up. And that just shows that here's, you've got the previous picture. You can put one on the bottom as well, and again, the leads won't twist up. So there you've got your J-type machine. However, there's a penalty though. In order to not have the leads twist up on the J-type CCC machine, you are fixed to one rotation around the sun gear for one spin around its own axis. You're fixed to a 1-to-1 ratio. It spins and it rotates, yeah? And you're fixed to that ratio, meaning you get one mixing step and one settling step per spin around the sun gear. Is that the optimum? Could it be that you need more mixing steps, fewer mixing steps? So this is the reason why you might want to look at a non-synchronous CCC, or this is the reason why we did in the research. We thought perhaps there are some phase systems where you want lots and lots of mixing and then only settle it occasionally, or just a small amount of settling. Or it might be that you have a delicate phase system, like the aqueous two-phase systems, where you don't want to mix it too vigorously, but you want a very strong settling force. So being able to alter that ratio of mixing to settling is what the non-synchronous CCC is all about. It's taking away from that 1-to-1 ratio and making it so that you can alter the amount of spin to the amount of rotation. But you might say, there's a penalty. You need a rotating seal, much like the CPC machine has. No, you don't. If you design, and this has all been done by the engineers, here's your J-type machine. If you design your flying lead with this clever mechanism just here, then you can alter the amount of spin to the amount of rotation without this lead twisting up. Now, you might not quite be able to get your head around it, I can't, but trust me, it works. I've used this machine and I haven't seen the leads twisting up, so trust me, it works. The engineers will tell you how it works, but the leads don't twist up. This is the engineering diagram of the machine. You need two motors, because you now need a motor in order to spin the coil, and then you need another motor to rotate it, because they'll be going at different speeds. And here's your lead path for the first bobbin that's just here, and here's the lead path for the second bobbin, just there. And the machine itself looks like that. So what does it actually do? Well, going back to synchronous CCC, standard J-type CCC, you've seen this picture before. You've got your 1-to-1 ratio, you've got the sun gear, you've got the planetary gear, and when you plot the path that this point P takes as it goes round, you get the shape known as a cardioid, loop-the-loop, and then a big high G-force, and a loop-the-loop, high G-force. So you get one mixing step and one settling step for every rotation, for every turn of the coil. When you can alter the amount of mixing and the amount of settling that occurs, you can get all sorts of interesting patterns. Here is the one we had on the last slide. This is with the 1-to-1 ratio. So here is the ratio of bobbin to rotor speed. And you can see that on E, it's at 1. So when you've got a 1-to-1 ratio, you get the cardioid shape. Yeah? When you have a 0, you get it like this. And I think I'm right in saying that will be an I-type machine. Am I right? This will be an I-type machine, which will be a bit like taking a beaker and swirling it round like this. Yeah? If you have a ratio of, now let me get this right, C, 0.33, you can see you've got a little mixing and lots of settling. What you're getting there is you're getting the rotor rotating 3 times for every mixing cycle. Here with, what am I looking at? F. So F here, you're getting 3 mixings for, let's have a look. You're rotating it 2 times, 3 mixings for 3, no, the rotor rotates 2 times for every 3 mixing cycles on this particular one. And on this particular one just here, you can see it's a minus value. The rotor is rotating in the opposite direction to the spin of the machine. Well, what we did was we took all of those different ways of operating, all 6 of them, and we injected 3 compounds onto the machine to see the separation. The 3 compounds were caffeine, ferulic acid, and vanillin, and here are the 6 different ways of operating, and you can see, I don't know if you can see it from the there, but it might be visible in your book. Here is the different ratio of rotor to bobbin speed, and we measured the stationary phase retention. Now, the 1-to-1 ratio is this orange line just here, and you can see in this particular case, you've got quite a good separation. But you get a 30% better separation with this one just here, which is a 0.67 ratio of the rotor to the bobbin. So by altering the ratio, you actually can improve the resolution of your components by 30%. By the way, this arrow is the D equals 0 point, or KD equals 0, which is the solvent front, which will vary according to the stationary phase retention. And this line here is the distribution ratio equals 1 point, which of course is your column volume, so it's fixed for all the machines. So the interesting thing with this machine is that by being able to alter the amount of mixing and settling, you could probably, you will be able to fine-tune your separation to your particular solvent system. You can well imagine that some solvent systems will require a vigorous mixing, but only a little settling. Others, much more gentle mixing and a vigorous settling, a very strong settling. But you could optimize your conditions and get perfect separation by having a non-synchronous machine, which you could then tune to the having the right degrees for your particular solvent system. So the next work on the non-synchronous is, of course, looking at aqueous two-phase systems. Now, my final mode of operation, special mode of operation, is called dual flow continuous extraction, CCC. It's a bit of a mouthful, but basically what we're talking about here is continuous processing. You want to have improved throughput at manufacturing scale, and this is with continuous processing, so it's almost true countercurrent chromatography. So far, we've talked about countercurrent chromatography, where you have a stationary phase and a mobile phase. Now, this is the countercurrent chromatography coil. You've just got to imagine that this is coiled up, it's spinning, there's waves of mixing and settling going on and so on. It's just diagrammatic of the CCC coil. But here it is in normal phase operation, where I've got a stationary lower phase, a mobile upper phase. I pump the mobile phase in, it comes out here, and my components will elute in order of their distribution ratio. Distribution ratio of 0, 0.3, 0.8, coming out in order of distribution ratio. Of course, the alternative is that I could make the upper phase the stationary one and pump the lower phase in, and then in case I'll do it the other way around, and my components will elute in reverse order of distribution ratio in this case here. I'll get D equals 10 coming out, D equals 1, D equals 2. That's assuming I keep the same ratio of for the same way of calculating the distribution ratio. The question you ask, why not introduce the sample in the middle? Why not actually just put it in the middle and flow both phases over each other? Then could you get out your low distribution ratio compounds at one end and your high distribution ratio compounds out at the other end, and be continuously introducing your sample into the middle? That was the question that we had. Does it work? Well, it looks quite complicated to set up, but it's actually not that bad. Because most countercurrent chromatography machines, particularly the larger ones, will have 2 bobbins. And the leads don't twist up on a synchronous machine, remember? And so here's your first bobbin, here's your second bobbin. And since the leads don't twist up, you can just take the lead out of the machine, add your sample input, your injector, and then put the lead back into the machine for the second bobbin. The only complication that you have on the when you're trying to operate it continuously is that at each end of the machine you've got both an inlet and an outlet. You are pumping liquid in and you're collecting the other liquid coming out. Now, in order to stop your liquid that's being pumped in just coming straight out of the outlet, you've got to put a tube within a tube in order to get the liquid started on its way down the coil, and then once it's started, it then just carries on going through the coil. So that's the only slight complication. Otherwise, it's actually a pretty simple machine to set up. So just to round off, I have talked quite a lot about CCC and the scale-up of CCC, and I hope I have shown you that it gets better as you make it bigger. It's a preparative technique. It's got a lot of advantages when you make it big, and there are, I think that it won't be very long before industry starts to realize that, and we start to see preparative CCC actually being used in pilot plants and in manufacturing plants. How big can it get? Well, we make jokes that they're not using the Millennium Wheel to very good effect at the moment, and what we like is a nice big coil put on it. You won't need to spin it very fast, remember? Big size, slow rotation, because you get the same G-force. So how big can it get? Well, we really don't know. Once again, I'd just like to acknowledge the team, because this has been a team effort. It's been work from all of these people. And then, once again, I'd just like to say thank you for your attention. And since I like penguins, I've got a picture of penguins, though. Thank you.